Dear students, let's proceed with our consideration of nonlinear electrical circuits. How we will consider such circuits. I have told you that if you have such designated resistance, capacitance, or inductance, it means that their parameters are nonlinear. And we will consider these nonlinear parameters on the example of usage of this nonlinear element in electric transformers. Here we have such a transformer with primary and secondary windings, which are located not just in the ear like it was considered in previous semester, but they are located on a magnetic core, on a steel with ferromagnetic processes, nonlinear ferromagnetic processes, and such design provides more effective transformers, more effective electric machines, because magnetic coupling of the primary and secondary windings here are better. Here we have windings of primary and secondary circuits located as close to each other as possible, and these windings are electrically non-connected. They are not connected just galvanically. They are connected via this core, and let's assign that number of turns of primary windings equal to W1 and of secondary winding equal to W2. And here flux F0 embrace all turns of both windings. You see, it is depicted here by dot lines. And lines of flux Fs1 embrace only turns of the first winding, and lines of flux, magnetic flux Fs2 embrace all turns of the secondary windings, and Fs1 and Fs2 called leakage fluxes. Let's write down now expressions for these Fs1 and Fs2 through currents in both these windings. Let's consider the flux F0, flux through magnetic core, has nonlinear dependence of currents which flow through these windings. It is called magnetomotive force, and it's equal to I1 W1 plus I2 W2. And flux Fs1, which connected only with primary winding, will depend on will be proportional to current I1 depend on it, and Fs2 depends on current I2 which flow through windings of the secondary coil. And let's write down that Psi1, its linkage of the first of the primary winding equal to Psi-S1, connected with this flux in the first Fs1 plus Psi-O0, its flux which is going through this core and connected with first winding. So it will be equal to Psi-S1 plus Psi-O1, and this Psi-S1 we will write it down like we write down all times. It is proportional to current I1, and coefficient of proportionality is inductance of primary circuit. And Psi01 will be equal to Fo, this flux, multiplied by number of turns of the primary winding. And the same equation can be written for the secondary winding. It will be Psi2 equal to Psi_S2 plus Psi_O2, or it's equal to Ls2, inductance of secondary winding, multiplied by I2 plus Psi_O multiplied by W2, number of turns of secondary winding. Let's consider that voltage U1 is applied to terminals of primary winding. As all time it is we applied voltage to primary winding and connect load to the secondary winding. So this U1 equal to sum of voltage drop across primary winding or ohmic impedance and sum of dψ1 by dt. It's a component which balanced applied voltage by induced flux linkage Psi1. So we can write down that U1 equal to R1 I1, because it will be ohmic resistance in any case. If we have some metallic made from, for instance, from copper winding here, and plus dψ1 by dt, because it's by Faraday's law. We do know that when we applied some voltage, magnetic change of voltage we change in time. We have as a reaction we have dψ by dt in this closed loop. And electromotive force dψ by dt, which is generated in the secondary winding, will be maybe written by the similar equation, but here we have no applied voltage, unlike primary circuit. Here we have no applied voltage, so we may consider that this counterbalanced EMF, which is generated due to flowing or due to magnetic flux through this magnetic core, we may consider that this minus dψ2 by dt is source of current which will flow across this secondary winding if it will be closed. It will be if some load will be connected between these terminals. So we can write down that it's equal to U2. U2 is voltage drop, R2 equal to R2 I2, where R2 is resistance of the load. So we can write down such equation for the primary circuits. For the primary unit, U2 equal to R1 I1 plus dψ1 by dt, and for the secondary winding it will be, we can write down that it will be R2 I2 plus U2, its voltage drop across resistance which connects these terminals, and plus dψ2 by dt. If we transact this dψ2 by dt to the left, it will be with minus. So it will be the same equation, but here we have U1 applied voltage and here we have U2, its voltage drop across load which connects these terminals of secondary winding. Oh, sorry. And now we can use relationship of linkage flux and the main flux of the transformer, and so we can rewrite got equation as follows. Maybe we will proceed. Okay, let's proceed something. So we can write down from this. Okay, we can substitute phi0 from here. You see, in the equations, for instance, this equation for the first winded, we can substitute here psi1 in such a form. Yes, psi1 as ls1 I1 plus psi0 multiplied by w1, and we've got here u1 plus r1 I1 here plus this equation. Instead of psi1, we substitute this equation. It will be ls1 di1 by dt. You see, it is here. And then instead of this, when we substitute here, it will be w1 dfo by dt. You see, it is here. So we just substitute this expression for psi1 in the expression for voltage drop across first winding here, and we've got such an expression. Then we should rearrange it. You see, we have common items, common summons here. It will be first summon will be just the same, and then we can write down that it will be ls1 di1 by dt, and we can depict this summoned as UF, voltage drop due to presence of this linkage which is comprise in media of magnetic core here. And the same we can do with the second equation, with this equation. If we substitute here psi2, this equation. Let's proceed in the next lecture. Yes, please. Bye for now. And for the next lecture we will proceed this material.